Okay, let's start again. So yeah, the slides are a little bit in wrong order, but I want to now go through supervised. Yes, supervised methods. And I guess we should start with neural networks first, and then do KRR, which is fast, and you will have time for exploring the exercises. So there is a notebook called Neural Network, Intro. There it is. Right, so what is a neural network? The notebook will explain a little bit in the details. So neural network is a function approximator. It's, you know, when you do a linear fit, your function is a line and you have two parameters. If you need something a little bit more complex, you can make it quadratic, cubic, and so on. But sometimes you have no idea what function you should use. So you can use a neural network because it's flexible, and in principle, it can approximate whatever function, in principle. They call neural networks because they are kind of inspired by brain, by neurology. The idea is that you have these input channels here. Maybe I should use the mouse there. So you have the input channels. They're just numbers for this case. These get connected to a hidden layer of neurons. The neurons will take the numbers from whatever's connected to it, crunch them with some function, and spit out an output. The output is then sent to another layer, which could be another hidden layer or an output layer. The output layer is just the last one, is just the name for the last one. You can have different designs, different amount of layers of different size. I mean, you can really, that's a hyperparameter of the model if you want. You can make it as complex as you need. Now we see how these neurons actually do crunch the numbers. So here's an example of a neuron J. It will get inputs from these guys, 1, 2, and 3. And each input is received, is weighted, is scaled by some factor, which is called WJ1, WJ2, and WJ3. So numbers go in and get multiplied by some parameters. Then the output of the neuron will be some function of the weighted sum of the inputs plus a bias. The bias is an internal parameter of the neuron, another one. So yeah, S is a nonlinear function. Usually people use a sigmoid, hyperbolic tangent, something nonlinear. Otherwise you get another linear model, and there's no advantage of using neural networks over other linear models. But you can, you're free to choose whatever function you want. People usually use hyperbolic tangent because it's fast to compute, and when you train these models, you need the derivatives of the error that the neural network is making with respect to the internal parameters, so W and B. There are schemes to compute these gradients, but if the function is easy to derive, then you can get it fast. So in case of hyperbolic tangent, the derivative is like 1 minus hyperbolic tangent square or something like that. So it's easy, you have it for free. If you're using some rectified linear unit, which is another function which is flat, and when the argument is positive, it becomes a line. So it's x for x positive and 0 for x negative. The derivative is either 0 or 1. So again, very fast. But in principle, it's an hyperparameter, what function you put in here. Anyway, you can see that by combining this kind of system here into some complex network, you can achieve a higher degree of freedom in modeling your function. Let's see it in practice. So we start by defining a model, which is this analytical function, and we add some random noise to it, just because. So the analytical function has this shape, and then noise is added to it every time we evaluate. Now we create a training set, which we create by evaluating this function in some points, in some random points in space. Now this is showing us the training set. Color would be the Z axis, the value of the function, and X and Y would be the inputs. This routine also computes some validation inputs. So we train on the test, but we check the performance on the validation. This is a set of points that the neural network never saw during training. We keep it from it just for checking performance at the end, for checking the accuracy. Because of course it's going to be good on the training. It's trained to reproduce the training. So it's kind of meaningless to check the accuracy on the training. You know it's going to be good. But what you want to know is how good your neural network will be on new data that you are going to show in the future. That's why we have the validation. In this case, we have 100 training points, 40 validation points. Good. Right. So now we use the scikit-learn to create a multi-layer perceptron, MLP. It's a fancy name for neural network. And it's going to have one hidden layer of neurons with 10 neurons inside. So it's exactly this architecture here with 10 guys in the blue layer. And there's going to be 2 inputs, which X and Y, and 1 output, the value of the function. So let's create this. We are going to use hyperbolic tangent as activation function of the neurons. And this solver Adam is just what algorithm we're going to use to compute the gradients of the error of the neural network with respect to the internal parameters and optimize them. It's some kind of stochastic gradient descent. Alpha is a regularization parameters. We're going to look at it in a moment. So what happens is that we have to calculate the error. So Y ref is the correct output from the training database. So what we know the value should be. Y is the prediction of the neural network, given a set of internal parameters. The error is going to just be the L2 norm of the difference. Simple, like least square. Okay? So far, so good. Now we have to calculate the gradient of this error function with respect to the internal parameters. And this includes the weights and the internal biases. There's going to be a lot of them. If you imagine this image, now you have 2 inputs, 10 here. There's 2 times 10 parameters for the weights. And then you are going to have 10 times 1 weights for this layer, plus 10 biases. So it's a significant amount of parameters. And let's do the training. Of course, all of this gradient calculation is taken care of by the library. This line here, you can comment out for now. If you want to try a different solver, you can just change the name. If you check the documentation of scikit-learn, it tells you what keywords are available, what algorithm you can use. So then we are saying we want to fit the neural network using these training inputs and these training outputs. This is the database we have. So the mean absolute value on training is this number, on validation is this number, and we can see the performance here. This is a regression plot. You have the correct output on the X and the prediction output from the neural network on the Y. Ideally, if you have a perfect predictor, every point aligns on the diagonal, on the orange line. So the points are now a bit off. We have a little bit of error, fine. You have to, if you're happy with the error, then you can move on. If not, you can try improve the model, maybe add more neurons, add more data, try different activation functions. That's it. So what regularization was? We added that parameter here, alpha equals 0.01. So the idea of training is to minimize the error with respect to the parameters. Great. In the end, we're going to have the best possible model that minimizes the error. But sometimes that's not good enough. How can it be? You might overfit your neural network. It means that it's going to get really, really good on the training set. But when you test it on some data that is a little bit different, it doesn't transfer anymore. It doesn't generalize. Imagine that you have, for a moment, forget it's a regression plot. Imagine that you have this data and you want to fit it. You want to do a fit of the data. Now, you could do a linear fit and you would get a line, great. But you may want to add more parameters and make a quadratic curve and do a quadratic fit of that. And you will get a better fit because you have more degrees of freedom. You have more parameters, you can do a better fit of that. If eventually you fit with a 40-degree polynomial, you can get a perfect fit. There's 40 points there. You can get a line that passes through all 40 points. It's just going to be super wiggly. But then when you test it on a new point, maybe up here, it's just going to fail brutally. Because the polynomial will just, degree 40 will just go to infinity. It will not generalize to new data. You messed up the model. You overtrained it. So you have a certain amount of data points and you have a certain amount of parameters. Usually if you have too many parameters and not enough data, there is a high risk that you will overfit. A way to counter the overfitting is to add regularization. And one way of doing it would be to add a cost function for having parameters. So the parameters W are connection parameters. So if a connection parameters is 0, it means that the number is not going to get through the network into the receiving neuron. So let's go back to the image. If a connection parameter here is 0, it means that this neuron is not using this input at all. It's multiplied by 0. Which means our network is simpler than what we devised originally. We have all of that connection and neurons in, but some connections are dead. So it's a simpler model. Effectively, some parameters are 0, they are not used. By adding this regularization factor to your cost function, so you will then minimize to get the best error plus cost of parameters. You are training to make the neural network better at prediction, but also simpler at the same time. So you're kind of forcing in Occam's razor. You're trying to make the model simpler. Of course, you are making it worse because it means you're not going to have the best possible minimal error. But you're going to have a model that can be transferred then on new data. It's going to be general. So usually that's what you want. The other way would be to have so much data that you have a small amount of parameters compared to the data. And then the fit is still meaningful. You don't need the regularization anymore. Because you have the data to sustain those parameters. You will never be in the case where you have 40 points and 40 parameters. And then you can fit everything. You will have so much more data. Questions? No? Was it all clear? Good. Unfortunately, there's no way to know what regularization here you should use. You just have to test a bit. If it's too big, it's going to kill the entire thing. It's going to give you that all the parameters are 0. You feed nothing. So this is just an introduction on how the neural network works. There's no exercises on this part. But now we are going to see it in action. We are going to use this neural, atom-centered symmetry functions dimer. So now we are trying to, we're going to use atom-centered symmetry function and try to fit a potential for just 2 atoms. So first of all, we just we just defined this cutoff function G1 These are the same we have seen before. Then we create the training set. We have a dimer, so 2 atoms, and we gradually pull them at we separate them different distances, and we have the true energy, which is given by a Lennard-Jones potential, which in principle we don't know. It's just data that we have. So that's going to be the energy of our system as a function of the pair distance of the 2 atoms. Now, what we will first do is create our parameters for the atom center symmetry function. In this case, we only have the G1 and the G0. We do not need the angular ones. There's only 2 atoms. So we are trying to keep it as simple as possible. So now for every configuration, we would calculate the G0 and we would compute all the G1s. And this is what we get. As a function of pair distance, we get the G0, G1, and the other G1. There's 2 because we have here 2 tuples. So the first one is from the cutoff, the other 2 are from the G1. Optional trick, we applied the Z-score. Again, we shift around the mean and we scale by the standard deviation, because you notice that there is one symmetry function that is a bit bigger than the others, or more than double. Same as unsupervised learning, when you do in neural networks, you might want to make it easier for the neural networks to learn parameters. And if you have some inputs that are huge and some inputs are tiny, it's going to have trouble. It's going to take longer. It might not find the optimal parameter set that easily. So just rescale everything according to your database. You just do the Z-score. Let's do it. And now you see everything is in the same numerical range. Easier for the computer. Then we can do the training. Again, we create a neural network with 5 hidden neurons, hyperbolic tangent as activation function, and then we just try to fit it. And it worked. When you will try to fit atom center symmetry function potentials by yourself, you will notice that it's not gonna work like this. It's gonna take you months of trying and sweating and crying. It's not gonna be this easy as the dimer. Dimer always works. Real work is real work. It's not this. So yeah, it worked quite nicely. You see the regression plot is really on the diagonal very nicely, but there's just 2 atoms in there. So let's not jump to conclusion. Exercises would be try to change the energy expression, try to fit something a little bit more weird. You can try to create a validation set out of this and try to just train it properly on the training and check performance on the validation. You can try to add more or remove atom center symmetry functions. Or you can try to have it compute the ACSF on a real molecule. Of course, training it is a different story. Anyway, this is something you can look at if you're interested in ACSFs and neural network potentials. Let's move on to neural network for total energy predictions. So this notebook here. All right, so
Filippo, just briefly, just a question. Are there rules of thumb for number of layers and the depth of the layers or number of nodes within?
No, there are no rules of thumb. There are a few very loose ones, like, but they don't really work all the time. They are just depending on the case. So sometimes you will see many networks that have few inputs, and then the first hidden layer is quite larger. So let's say you have 10 inputs and the first hidden layer is 20 neurons. So information gets expanded. And then progressively, as you go deeper and deeper, you have layers with fewer and fewer neurons until you reach the output layer. That's a very usual design. Why is like that? Well, someone saw it in a dream. There's no reason. So the reason why you would put multiple layers, it's because you want to crunch the numbers more and more. You want to add more freedom. But that's just it.
There's another question. Why do we need biases? And could you give any physical significance to them?
Why do you need biases? It might still come from the model of the brain. Some neurons are just firing even if nothing gets in. So you have this. So if the neuron gets nothing in the input, it might still activate, and it just numerically just gives additional freedom to the function you put. So if all the inputs are 0 and you don't have any bias, you can only expect 0 in the output. Because all the numbers are 0, get multiplied by the weights, they're still 0, they get summed up, 0, and then you give it to the hyperbolic tangent, 0. But if the true answer of a 0 input is not 0 output, then you might need the biases.
So many hyperparameters. There is the width and depth of the network. There is the strength of the representation and the rate of the LM algorithm. So many hyperparameters. You get easily, when you are approaching a new task, thousands of white root guesses for the initial configuration.
Mm-hmm.
Would you suppose any strategy to start with by guessing those configurations?
So the question for the remote people, there's a lot of hyperparameters, the shape of the network, the activation functions, the weights, the biases, the regularization factor, what else? The algorithm you use and the parameters of the algorithm you use to do the optimization. So how would you sort through all of these hyperparameters and find what works? Well, for the algorithm, for the minimization algorithm, you can use the defaults and check if the defaults work. Usually the problem might be from the choice of activation function. So you might want to try ReLU instead of hyperbolic tangent. It usually trains a bit faster, so it's faster to test. Regarding the shape of the network, the amount of neurons, yeah, just go with the feel. Ideally, you want fewer parameters, so the network is simpler, but you also want it to be accurate, so more. Try to find a compromise by testing. Yeah.
Is there any studies in material science?
Are there any studies where they show how to systematically Bayesian networks are a bit different concept. Yeah, of course. You could basically train a new machine learning model to predict what this set of hyperparameters would give you. And then it becomes meta-fitting. You're fitting the fit. It never ends. No, I'm not aware of studies where they show, because it depends on the data, it depends on the application. There may be, but I'm not aware. I usually just test and see. In the end, when I get an accuracy that I'm comfortable with, I stop. And usually that doesn't happen easily.
So if we increase the number of nodes or neurons, is there a risk of overfit?
Yes. More parameters higher chance of overfitting if you don't also increase the amount of data. You can always apply the regularization and it will kind of compensate for it if it can. There are many schemes for regularization. I just showed this one about adding a cost to having parameters. TensorFlow has some nice routines where you can do this skipping layers. In convolutional networks, I think it has some scheme where you can decide to randomly completely exclude a layer and send the output of one layer 2 steps forward instead of 1 step forward. There is dropout, where when you're training, you can kind of kill a connection or a certain percentages of connections randomly, so that the training will become robust with respect to them not being there. Yeah, they all do the same thing. They try to make it simpler. Okay, so here's the problem at end in this notebook. We have a bunch of the descriptors for a lot of molecules. And I perform all this calculation at the couple cluster level. So we have the energies of all these guys, and we have descriptors. So let's try to fit a neural network that operates on the descriptor and outputs the energy of the system. We have pre-calculated for you some descriptors. We have atom count. This is the simplest descriptor you could think of. It's counting the different species. Bob, bag of bonds. It's basically counting bonds. So if you have a carbon-hydrogen bond, that's going to increase by 1 descriptor. If you have carbon-carbon bond, it's going to increase by 1, another feature of the descriptor. So you count all these different bonds of different types, and the string of numbers becomes your descriptor. We have SOAP, which is obtained by either by summing all the contribution for all the atoms, or by making a mean, or by taking a SOAP expansion around the center of the molecule, the center of mass. We have MBTR, and we have Coulomb matrices, which you can find in the Matthias Rupp paper about kernel ridge regression on this data set here. So let's start with Coulomb matrices. If you change the variable here to something else, you will load a different data set, so it's easy to do switches. Let's load data for Coulomb matrices. Here it explains what they are. They are matrices of Coulomb interactions between the atoms in the molecule, just by looking at the nuclear charges. You have the expression. Every element is basically the Coulomb energy of a pair. And on the diagonal, you have some kind of van der Waals-ish formation energy of the atom, some Z to the 2.4, something related to some physics. Great. Then we load the data. We split it into training and validation. The splitting is done here. So we take 9,000 samples for the training, and which is the first 9,000 from the database, and then we take from 9,000 to 10,000 for validation, just 1,000 of them. And yeah, now we see we have 9,000 training samples, 1,000 validation samples. Each one has 29 features. Those are the eigenvalues of the Coulomb matrices. It's not really the true Coulomb matrix, because the true Coulomb matrix is not invariant under reordering of the atoms. Every row corresponds to an atom. So, but you can get around it by taking the eigenvalues. So those don't depend on the order of the rows and the columns. Then we create a neural network with a lot of beef. So there's going to be 4 layers in the middle, 1,000 neurons, 250, and 50. And the final one is going to be 1 output neuron with the energy. Here we have some parameters, algorithm, activation function. And then we do the training. The kernel have died. Dead kernel, thank you. All right, let's try it again. Hopefully on your computers it didn't die. Do you have some limitation on how much computer power I can draw from? All right. Yeah.
I'm not sure if it. Oh, we increased the memory to 1 gig and it started.
I'll make it smaller. Okay, I have to rerun. The kernel died completely, so. Okay. Seems like it's doing something. Yeah, also there is a lot of data. I probably should start with 1,000 or so. This is gonna take a while. Questions in the meantime? If you have run the one with 1,000 neurons in the first layer, it's probably still there. Okay, done. Right, it didn't learn anything. It just predicted one value out, and that's it. So our model is quite bad, or the training algorithm is bad, or the data is bad. You have all of these options now. I would suggest the first thing, simple, that is just replacing hyperbolic tangent with ReLU, rectified linear unit. So let's run it again. Parabolic tangent is great, but it has its limitations. So it's, you know, the output is always constrained between -1 and 1. So perhaps for these energy calculations is not what you need. Super slow. Did you get anything? Did it learn? Yeah, that's normal. All right. Looks quite better, right? No? Are you not deriving happiness from this regression plot? So it's mostly okay. The error on validation is 1. I guess it's 1 Hartree. Yeah, it sounds bad, but validation. This is plotting the validation ML output. Let's see here. Yeah, it's doing the validation. So you'll notice that yeah, in the ends here, high energy, low energy, it's not as accurate, and that is normal. Like there's not that many molecules in the training set at those extremes of the energy space. So it didn't learn those very well because there were not that many samples. It's expected. Now here's a histogram of the error, if you're interested. Now, you can make it better by by making the neural network bigger, using more data. It's going to take exceedingly long for this tutorial to do so, but you can take this notebook with you at home and you can play with it. So let's try something simpler. Let's use a different descriptor, bag of bonds. This is a simple one. So it's just 20 numbers for every molecule. It's much smaller. These are the normalized counts. Since the model is simpler, we can try to make it simpler here too. So the neural network doesn't need to be that big. Perhaps let's make it like this. So I create a new network. I make it one layer smaller. In the small hope that it's not going to take too long. In reality, you will not use scikit-learn. You will probably use TensorFlow, which is more, it's more in every sense. It's better. You will probably use GPUs, which they're also more. So you can get it done in a reasonable amount of time. Perhaps. Yeah, sorry, I changed them. Before it was 100. Or the original in the notebook was 1,200 something something. 50. Yeah, then I reduced it to 100. 40. For when I actually worked, and now I use this one. Worked. And it's even better than before. Amazing. We used a simpler descriptor and we got a lower error, less than half an R3. This is magic. It's like dark arts. Like, why? I put less information in, but well, maybe the less information we put in, it's more on point. Like, what the hell are those eigenvalues of Coulomb matrices? Those are whatever numbers, right? These are actually related to the physics. It's directly, the information is directly there. How many carbon-hydrogen bonds there are in my system, and there's going to be a feature there. How many hydrogens, how many, so the descriptor is more compact in a way. So it's going to be easier for a smaller network to figure out the correct parameters and give you a better answer in the end. Yeah. This is great. What you can do as exercises, try to compare descriptors, try to find these trends. Also, you can combine it with principal component analysis. You can load the MBTR descriptors for these molecules and filter them out. You can also use TS&E instead of PCA if you prefer. You can just do a bit of bricolage of these notebooks, try to make it work. Yep. So next, we are going to try a local atomic property predictor. So we're going to use neural networks to predict atomic charges. In this case, we have descriptors of atoms, and we're going to try to predict Mulliken charges. The problem is not simple. So in this image, you can see these histograms. This shows the amount of S electrons for different carbon atoms. in different environments. So in the database, of course. The black histogram here would show you the Mulliken charge of CH3 groups. And you see it's quite complex because it depends on what's attached to the CH3. So this is CH3 with carbon. Only carbon is attached, but it could be a CH1, a CH2, another CH3, or a carbon with then another chain with some oxygen. We don't know. So all of that will actually affect the result, the amount of electrons that are going to go on that carbon. So it's quite a complex problem to figure out using simple shorthand rules. Here's a breakdown of just that black histogram. So we are asking what's the charge of the CH3, and here is connected to a triple bonded carbon. It gives this distribution here. When it's connected to this kind of group, we get these yellow components, and so on. It's really not even a second order problem. You would have to look at the entirety of the molecule of the bonding network to figure out all this complexity accurately. So let's have a neural network do it. Again, we have descriptors. You can choose by changing the name in a string. We have bag of bonds per atom. Bag of bonds second order. It takes into account what's bonded to the first bonded neighbor. We have atom center symmetry functions. Graph neural network. This is something we developed in my company. We have SOAP and MBTR. You can switch the atom type you're interested in. So in this case, Z equals 6 is carbon. Let's look at the bag of bonds, simple one. Okay, we load the data set. I'm gonna make it 1,000 because it's gonna be faster to train, but you can experiment with bigger. Okay, so now we have 1,000 training sample, lots for validation, which I suppose you can change the number here for validation. Yeah, so you only use 1,000, otherwise it's gonna take a long time to evaluate. And also here. So I added samples plus 1,000 here, so it's gonna take only a few for validation. Here we are applying the Z-score, and then we create the neural network, which kill the kernel. I have to start from the beginning. Great. All right, then we train it. And we have our results. It's a simple descriptor. It's a small network. Perhaps the result is not too good. We get 0.06 electrons error per atom, per carbon atom. You can try to make it better. That's probably one of the exercises now. Compare descriptors, try to optimize the neural network. You can try to make a plot, training set size, accuracy versus training set size, and see when you reach the kind of limit that you have trained as much as possible. Again, combined with principal component analysis or TNSE, TSNE. Or you can put it all together and try on a new molecule and see. So this will be combining all your knowledge from the other notebooks. So this loads a molecule, which again is this one. You can try to now calculate the descriptor of this one and feed it to the neural network and make a prediction for these atoms. Or you can try to analyze the chemical environments from the descriptor instead of from the drawing of the molecule. Nice. Oh, but we need to know the descriptor parameters for that. Well, that's actually true. If you do bag of bonds, then you don't need the parameters. But yeah, you're right. So maybe don't look at that exercise unless you're ready to do it for the entire database and retrain everything completely. Yeah, you're right. You need the descriptor parameter, which I don't remember now. But bag of bonds, Coulomb matrices, you should be able to calculate without parameters. So the last thing I want to show before I just leave you to your own devices is the genetic algorithm notebook. So now we have seen for training neural networks, you would use this gradient approximation, these gradient algorithms, where you calculate the error, the gradient of the error, and you walk the gradient to minimize the error. But sometimes it's difficult to apply. For example, if you're training these neural network potentials for atom center symmetry functions, it's not that trivial. It's not as simple as just sticking the entire thing in TensorFlow, and there is some extra step, which will be all of the neural networks then have to be combined. You have to sum all the outputs to get the final energy, eventually doing a derivative to get the forces and train for them. It's not something built in TensorFlow that easily. And the Baylor group didn't really give us the code to do it ourselves yet. So we have to brute force it our way. And one way you can train those things is with genetic algorithm. So the idea is to simulate evolution, and what you're evolving your neural network model towards a good solution that will minimize the error, hopefully. So how does it work? We start with a population. We would have a population of models. They're all going to be randomly different. We are going to evaluate how well they do, and then we're going to mix the good ones. That's how evolution works. Now, in this case, we have a toy problem. We have a compound oscillatory signal, and we have its value at different points in time. We would like to extract the components, the Fourier components. But we are not so good at FFT or nonlinear fitting, so we try brute force with genetic algorithm. Now, every element of the genetic population is going to be a model, which is going to be represented by a set of numbers, which are the amplitudes of some plane waves. So an element is going to be a set of this A1, A2. We're going to have 5 of them. We can choose. So the population size is going to be 100. We are going to have 100 models. Each one has 5 parameters. The parameters can be between -2 and 2, just because. We create an engine. This is some Python library I quickly wrote. You find it in the folder there. This tau, we'll come to that later. Then we load the data. This is the signal we are trying to fit. Now, the genetic algorithm would evaluate how good our models are at reproducing this data. And then it's going to sort them. The best one are going to be first, and then gradually the worst and worst. To simulate evolution, you would have to select elements from the population at random and mix them. And the selection process has to be biased by the fitness. So good elements have a higher chance of being selected to generate the new offspring generation. And the one way of doing it is to apply exponential distribution, which is governed by this tau parameter. If we put tau equal 1, the probability distribution for selection is going to look like this. The first element in population is going to have this probability of being picked, and the last one, the worst, is going to have this probability. If you make the tau bigger, your distribution becomes more and more biased towards good elements, which means you're going to have a fast evolution. Eventually, it's going to be so sharp that the bad elements are never even going to be looked at. So you have them in the population, they die immediately. They never produce anything. Very fast evolution, not necessarily what you want. Because if the bad elements die immediately, evolution will converge, and every element in your population will look exactly the same very quickly. So then it means your genetic algorithm will stop improving. It will improve very slowly through random mutations. If you want to have maybe better results, you might want to put this number a little bit smaller. Maybe this is too much. 1 was good. So the bad elements still have a chance of being picked, and evolution will not converge so quickly and slow down in the beginning. Of course, it's going to evolve slower. Let's keep it like that for now. Mutation rate, how often elements are completely randomized. And this is the function that evaluates the fitness. This is something you have to supply to the genetic algorithm. You have to tell it how to evaluate how good the elements are. And you see what it's doing is just taking the parameters. Those are amplitudes, A and amp there. It's just summing up the plane waves with the amplitudes taken from the DNA of the elements. The DNA is just the parameter set. And then it's calculating the least square error, L2 norm. The fitness is going to be minus the mean of this error. Higher fitness means a good model, low fitness, bad model. So the best model you could possibly get would give a fitness of 0. That would mean it's perfectly fitting all the points, 0 error. And now we let it evolve for 30 generations. And you see that in the beginning, yeah, you get some error. This is the fitness of the best element. And gradually, through the generations, this fitness improves. Let's make a plot. So it's stochastic. You see that the fitness here goes up and then down and then up and down. You see these trends everywhere. It's stochastic. It's a stochastic algorithm, which means it's less likely to get stuck in a local minimum. When you use those LBFGS, Adam, gradient descent, there's always a chance that your neural network parameters will just converge to a local minimum. It's not what you want. Genetic algorithm doesn't converge to any minimum because it doesn't have any knowledge of gradient. It's just trying. And somehow the better ones have a higher chance of propagating their parameters to the next generation. Eventually, this looks like it's converging, and the entire population is becoming sort of similar in performance. The best and the worst are very close to each other. Let's see what they are. These are parameters for the best guy. And when you look at it, yeah, it kind of looks like the original signal we had. This is with 30 generations. We can just run it again and give other 30 generations. And now it's a little bit better. You can keep it running for thousands and thousands of generations, and eventually it will get even better. You just stop when you're happy or when you run out of computer time. Now, this was fast because it's a simple example, but when you have many parameters, you need a very large population. You need a lot of computer resources to evaluate all those elements and repeat this calculation for thousands and thousands of generations. So yeah, it's brute force, sort of. So it will work, but it will take its time. And it's cool. You can train AIs, and there's a link here if you want to. Maybe in your browser will load. There is an app, and there is a little submarine that you can try to challenge. This is entirely learned with genetic algorithm. So it learned how to, there is a tunnel, there are sensors, these are the inputs, and the neural network inside the submarine has learned how to navigate the tunnel based on what these sensors see. It's trying to avoid the walls of the tunnel. And I didn't code anything. I just let it play, and it played the simulation millions and millions of times, and it learned from it. And you can do the same with your neural network or material science. I could look at it all day, but not today. So yeah, this is it. There is a very beefy exercise here, which means try to put together a code that will train atom center symmetry function potentials from a database, which is given in that file. You have a bunch of molecules with completely different molecules, and you can try to train atom center symmetry function to reproduce the energy of those using genetic algorithm. That's all we can do, since Baylor didn't give us his code. So hopefully he will look at this video and give us his code. Okay, so now you are free to try the exercises, and if there are any questions, I'm here. Okay, so yeah, for genetic algorithm, what is best? Number of generations equal 30, some number, and then you repeat many times. It's the same. I just put 30 generations there because it takes a small time to do, and we can check results quickly, iteratively. And we can see if it needs a bit more. Let's give it another 30. The thing is that when you do it again, it starts from the last population that was calculated. So it's not restarting, it's just continuing. It's the same in the end. If you just don't want to do it, if you have a better genetic algorithm code that will print every generation, let's say, as it goes, then you don't need to do this. You just set it up for 1,000,000 generations and wait. And every so often you can check the output and see if it got good or not. Okay, so we have another question. This is a very good one regarding the neural network. Why activation hyperbolic tangent failed to train the set, but ReLU worked? Okay, so let's see. Now you can all admire my artistic skills. And I'm gonna draw the two functions. So the hyperbolic tangent will go something like this. It's symmetric, but it's capped between +1 and -1. The ReLU, which I'm going to make red, is 0 when the argument that comes in is negative, and then it's linear when the argument that goes in is positive. So if the energy of those molecules is not contained between -1 and 1, it was like -7 R3 up to what, -200 R3. So it would never be able to be fitted with those. Of course, the output of those output neuron comes from the linear combination of the previous layer, and that's why it was giving some, and then there is the biasing. So in the end, it was not always -1 and 1, but it didn't learn anything because there was not enough freedom to crunch the numbers enough, probably. Everything was squished between -1 and 1, and maybe it just needed more room to wiggle. There's also the possibility that maybe ReLU could have, hyperbolic tangent could have worked. It's just that we didn't use the correct algorithm. Maybe with LBFGS it might have worked. You never know. But my feeling is that those energies are like big numbers. I would see no reason to confine the network internally between -1 and 1. That's something you do when you have a recurrent system and you don't want them to diverge. But this is not a recurrent system. It's just a feed through, feed forward. So input, output. If you would have to feed the output back to the input and do some kind of recursive thing, then you probably want to keep it constrained. But in this case, just give it as much freedom as it wants. We have a question from the audience. On a neural network, there are many parameters to play with. Descriptor, hidden layer size, number of layers, activation solver. Yeah, in real life, how would you do? Yeah, you just test. You just test. Yeah. When I did it, it's very frustrating. You just have to try and try again. And in the end, the problem is usually the data, not these details here. So first check the data. With neural network topology size, you just start from small and gradually make it bigger and bigger and see where it goes. Regarding activation function, well, you test, probably you would test hyperbolic tangent and ReLU first. Yeah, usually ReLU works. Hyperbolic tangent might work too, but there is no rule of thumb. It's just testing. In principle, these things are kind of robust. They will sort out the complexity if they can. So it doesn't matter if you put 20 neurons or 25, you're still going to get something if the data is good enough that you're supposed to get something to begin with. Okay, so someone found a software package, N2P2, from the Lagos group. Great. So there is one. Okay, yeah, good. So you don't need to brute force it, maybe. Thank you. Should share this. We had a question from someone here in the room. The question is whether this nonlinearity in this function here is enough Yes, it is. Is it possible to do something on this side and apply some more evolved function to these inputs at that stage? And the answer is yes, it's possible, but you would have to write your own code to do so. This part of the machinery here, this is linear part, where you just multiply by a number. This part here is basically matrix vector multiplication internally in the software, which is very fast. And that's why all the software packages use this architecture. It's simple. And all the nonlinearity is packed into this activation function at the end. If you're willing to write your own code, you can do whatever you want. There is a very simple example of how this neural network breaks. So imagine that you have two inputs. Maybe I can draw it. So we have two inputs and one neuron in the middle. Is this on? Yeah. Right. And we have the connection here. So this is very simple. All right. Let's imagine that the true output that you want is x times y. And this is x, and this is y. So the true function you're trying to approximate is the product of the two inputs. There's no way any neural network will ever reproduce this in every range of numbers. You will need an infinite neural network. There's just no way, right? You can feed this to as many neurons, as many layers as you want. It will never capture the true function. It will only approximate it in range where you have training data, but it will not learn the true relationship. And that's because the way the numbers are crunched, they're just multiplied by constants, sum them all up, add a bias, and squish it through a hyperbolic tangent or ReLU. It doesn't matter. It's never going to work for all numbers. It's only going to work locally on some range. And if you make the neural network bigger, eventually it will work on a big enough range that you care about, but not always. If you want, you would have to make some kind of genetic program, a genetic tree of operations that is more flexible than a neural network. Then you can, but it's way more difficult to train. Yeah, orders of magnitude more difficult to train. Yep. Yeah. Yeah, so the difference between a regression model and neural network would be that the regression model is always a fit, while the neural network could be used to learn the true relationship between the inputs and the output. But now we are seeing that there are some relationship that this thing cannot learn. Well, there are some that it can and some that it cannot. No, if you look at the mathematics of KRR, you will see that it's always a kind of fit. Yeah. If your training database is complete, then you will never go in extrapolation, and then it would always work. If you can achieve that, then yes. So would the neural network, right? So why not using the ReLU or hyperbolic tangent activation functions with a linear layer at the end and make the network learn any output? I think even if you have a linear layer at the end, which is often the case, the output layer usually doesn't have the activation function applied. It just sums up and multiply by the weight and add the bias, and that's it. No S function. It will still not be enough to reproduce that particular relationship of product between the two inputs in every possible numerical range. It's just mathematically not there. You can approximate it to some precision in some range, but not always.